Hey, Fidelity, how can I remember to invest every month?
With the Fidelity app, you can choose a schedule and set up recurring investments in stocks and ETFs.
Oh, that sounds easier than I thought.
You got this.
Yeah, I do. Now, where did I put my keys?
You will find them where you left them.
Investing involves risk, including risk of loss. Fidelity Brokerage Services, LLC, member NYSE, SIPC.
With threats to our nation waiting around every corner, adaptability is more important than ever. When conditions change without notice, quick strategic thinking is crucial. And with obstacles consistently impending, determination is essential in overcoming them. It's this willingness, decisiveness, and resilience that sets Marines apart. With our fighting spirit, we don't just fight battles, we win them. Marines are the constant our nation counts on to fight the unknown. And through adaptable problem solving, we do just that. Learn more at marines.com.
This may be the smartest guy in terms of raw intelligence that I've ever had on the podcast. Sean Carroll is a great physicist, but also a great writer of physics. And he really attempts to explain to me quantum mechanics and the difference between quantum mechanics and classical physics. I kind of make some analogies about how this could apply to my personal life, of course. And I also make a fool of myself and pitch an idea that I think could win the Nobel Prize. But if you listen to this podcast, you will know more about quantum mechanics than you did before you listened to it. But I have to admit one thing. Sean Carroll, so he's a professor, lives in Maryland, again, super physicist, has written a bunch of books. There's another Sean Carroll who also lives in Maryland, who's also a very smart guy. And while I was preparing for this podcast, I didn't know the difference between the two Sean Carrolls. So I read a bunch of books by both Sean Carrolls. So, Jay, we're going to have to find the other Sean Carroll. So today is Sean M. Carroll, but there's a Sean B. Carroll who wrote a book called A Series of Fortunate Events about how it's basically all the science behind how lucky it is that mankind or humankind exists. And it was a fascinating book, just as fascinating as Sean M. Carroll's book. And I read both to prepare for this. I only later realized it's different Sean Carroll. So we got to get the other Sean Carroll on the podcast as well.
This isn't your average business podcast, and he's not your average host. This is the James Altucher Show.
Sean, I've been super excited about this episode. I've always been interested in your work. Your 2020 book, I'm forgetting the title, even though The Biggest Ideas in the Universe, a really great explanation of physics in a way that you attempt to make the common person understand, but it's a very hard book. But now this book, The Biggest Idea in the Universe, Quanta and Fields, just came out. Also a very difficult book. It looks like, I'm holding it up for people who are not watching. It looks like a normal popular science book that one should be able to pick up in the bookstore and read, but it's very difficult to read. I'm not saying people shouldn't buy it. What I did was I kind of skipped equations and when my eyes went to paragraphs that I could understand and parse, and I got enough out of it that I enjoyed the book. And it
Good. I mean, it's meant for people who want a little bit more than most popular science books. It's the peek behind the curtain where we show you the equations and try to explain how they work. But like you say, it can be read at different levels with enjoyment.
I mean, I would describe myself as someone who's interested and curious at a pop physics level. Mm-hmm. You meaning, okay, I like to read about all the different theories for how the universe began, of which you have your own particular theory. And I like to read, about small particles and how they entangle with each other and Schrodinger's effect. And I like to try to understand these things at a high enough level that I can explain it. But I feel like every year or so, I need to read another book just to remember everything I learned, because it's very easy to forget too the nuances in these fields.
Well, and also when you're hearing it as metaphors and analogies and stories, they don't quite stick with you quite as much. I mean, it's great, and I do it myself. Most of my books have no equations in them, and I try my best to explain to a wide variety of people. But if you're a physics student, of course, you sort of work through things yourself. You do homework, you do problem sets, and you sort of live inside the physics, and that's how you really absorb it.
What I love about physics in general is that, you think of science as something, you have a theory, you test it, and now you know if it's true or not. And you don't always know with 100% accuracy. So for instance, medicines is famously like, you have a theory, this medicine will work, you test it, and with a high degree of probability, you could say this medicine works, or this medicine doesn't, or this medicine's safe, or this one isn't. But with chemistry, in general, you can put two elements together and see if it explodes or not. So you have a theory that explodes, and then you're done. But with physics, it's amazing how much we know and how little we know. And it's really that cliche that the more you know about physics, and this is true for the physicists, the less you actually know about the universe. Would you say that's somewhat true?
Well, I would say the more you know about physics, the more you know about the universe, but the more you appreciate how much there is that you don't know about. I mean, it's a tough thing to get exactly right because, like you say, we do know a lot about the universe. Apples fall from trees. That was true for Isaac Newton, still true for Albert Einstein, still going to be true 1,000 years from now. But maybe our explanation for why apples fall from trees is very, very different in those eras. So we're going to keep changing and improving and getting better at understanding the universe. And along the way, we'll realize there are whole big questions we didn't even have the capability of asking earlier on. So there's still things we don't know.
Well, let's start with that example. So the apple falls from the tree, and the high level reason, I guess, is gravity. There's something called gravitational force that a bigger object or an object with more mass exerts some energy on smaller objects that draw that smaller object towards it. So the apple is smaller than the Earth. Humans are smaller than the Earth, so we can stand on the Earth without flying off into space. If there was no gravitational force, we would just fly off into space. And what's the next layer down where it might start to get confusing?
Yeah, no, you're exactly right. So what you just told us about is something like the Newtonian version of gravity. Sir Isaac Newton back in the 1600s set up the whole scheme that we now call classical physics, including gravity, according to which there's a force, the gravitational force. It pulls things together depending on their masses. Now, Einstein comes along in 1915 and says, I have an entirely different way of describing that process, namely that space and time, where we live and the time parameter that tells us when we are in it, are combined into one four-dimensional space-time, and that space-time is curved. It has a geometry, and the curvature can change. It's dynamical. It's sort of like a wavy ocean rather than a solid structure. And that curvature of space-time is what makes us think that there's a gravitational force pulling on things. When the apple falls from the tree, Isaac Newton says the gravitational force of the Earth pulled the apple. Einstein says the apple is doing its best to move on a straight line, but there are no straight lines because space-time itself is curved, and that's what we perceive as gravity.
See, right there, I completely can't picture it or understand it. Even though I've read that a gazillion times, I don't really understand how when I'm looking across the room, space-time doesn't, or space, let's say, doesn't look curved. I can't really see time. So when I drop something, it really makes sense. Why did we need a new rule? Newtonian rule was fine.
No, that's perfectly legit. I mean, that's why you had to be Albert Einstein to figure it out. And that's why it took hundreds of years after Isaac Newton to figure it out. And the answer is it comes in a large number of steps. He thought in the 1600s or 1700s that Newton was just right, that he more or less had figured it out. We needed to get some details right and dot some I's and cross some T's. But then sneakily, in the middle of the 1800s, came electromagnetism. James Clerk Maxwell and Michael Faraday and other people said there's this thing called the electric field filling space and something called the magnetic field, and it explains how things move around. And people noticed that there was an inconsistency between the way that space and time behaved according to electromagnetism and the way it behaved according to Newtonian physics. And so Einstein and others in the early 20th century figured out Maxwell was right. The electromagnetic way of looking at things is the more important one, and it combined space and time into one thing called space-time. And then Einstein sort of went backwards and said, okay, we need to reinvent gravity. If we've reinvented space-time, we need to fit gravity back into this framework. And it took him 10 years to figure it out, but he eventually realized it's the curvature of space-time, the geometry of space-time that gives rise to gravity. And he, on the basis of that, made new predictions. He predicted things that we hadn't yet observed. He explained things that we had observed but were puzzled about. He introduced whole new ideas, like eventually we invented black holes and the Big Bang and gravitational waves. And so it's just an attempt to make everything consistent, right? Attempt to make everything fit together, both experimentally and theoretically, leads us to some crazy non-intuitive places in physics.
Well, first, how was electromagnetism different than the Newtonian view? And I'm sorry, I'm going to ask naive, dumb questions, but I'm really trying to get to the heart of your book, which unravels all of these things, but with heavy science and I want to get there.
Well, it's because what people noticed, and I'm going to sort of mess this up because I don't remember exactly what the historical experiments were, but it's basically that if you have an electrical charge moving, you create a magnetic field. So you have an electric charge all by itself, like an electron just sitting there, one-point particle. It has an electric field just like the Earth has a gravitational field. In fact, it's the same exact mathematical structure. But then you make that electron move, and suddenly it looks like a magnetic field, not an electric field. And so you take that idea that somehow moving charges make magnetic fields, stationary charges make electric fields. And then if you're Einstein, you remember, but what do you mean move? What is move compared to what? That's why it's called the theory of relativity, because he points out there is no absolute motion in the universe. There's no notion of this is what motion is once and for all. It's just you relative to me or you relative to the Earth or whatever. And so if that's true, if there's no such thing as absolute motion, but an electrical charge in motion gives us a magnetic field, then secretly the electric field and the magnetic field must be the same thing, just looked at in different ways, looked at from a stationary observer versus a moving observer. And that's what set us on the road to saying space and time themselves are not absolute. They're two different parts of one four-dimensional space-time.
So are gravitational fields, are they the same also as magnetic fields? Like what turns a magnetic field now into a gravitational field?
Magnetic fields and electric fields are unified as far as we know. Gravity is something different. It's similar in many ways. In fact, if you get deep into general relativity, you will learn about gravido-electric fields and gravido-magnetic fields. But for the most part, in our everyday lives, we don't need to worry about that. The point is that gravity is also a force of nature. It just comes from somewhere different. In the case of electricity and magnetism, particles have charges, right? The electron is charged -1, the proton is charged +1, the neutron is 0. And that's very special. We can sort of take positive charges and negative charges and cancel them out. And that helps us manipulate electromagnetic fields to set up waves, right? Waves in electromagnetism are light or radio waves or other things that we use in our everyday lives. Gravity is a little bit kind of duller in the sense that all the particles are just positively charged. They all have mass. Mass is the source of gravity. There's no anti-gravity particles out there. So gravity is actually in some sense easier. It just piles up. We feel the gravitational field of the Earth just because there's an awful lot of atoms out there in the Earth.
Now, with Einstein's new theories, or new then, with Einstein expanding on electromagnetism to include gravity, when he says it's all space-time, does that mean he's saying gravity doesn't exist? It actually, what we thought was gravity is this space-time curvature?
Yeah, I mean, that's a great question because professional physicists disagree about this. I think the right way to say it is Einstein offered us a different way of talking about gravity, in which gravity is really a feature of space-time itself, rather than, like electromagnetism, a force living within space-time. So gravity is a bit more fundamental, a bit more built in to the fabric of space-time itself. So therefore, you don't have to talk about gravity as a force. You can just talk about it as the curvature of space-time, and that's fine. But you know what? At the end of the day, that's just a way of talking. It's just a language preference that you can use. If you want to talk about the force of gravity, even in Einstein's universe, you can do that. If someone says the force of gravity is pulling the apple down from the tree, don't give them a hard time. It makes perfect sense what they're trying to say.
But this is where it does start to get murky in physics land, I think, because, for instance, even in the book, you have a footnote where you say, we know gravitons, so particles that are formed by gravity, we know that gravitons exist, we just have never measured them. We've never seen them in an experiment. Just like we know photons exist and we've seen that, we also know gravitons exist. But if it's just this kind of feature of space-time, then gravitons wouldn't exist.
No, they would, because even space-time has to obey the rules of quantum mechanics. So the thing that I think, like you said, physics is not done yet, where there's still mysterious things. There's questions we don't know the answer to. And one of the biggest ones is how to let gravity, according to Einstein, the curvature of space-time, play well, get along with quantum mechanics, which is the subject of book 2, the Quanta and Fields book. And we're very good at describing all of the other forces of nature in the language of quantum mechanics, electromagnetism, but also the nuclear forces, the behavior of matter, and so forth. Gravity, we don't yet have a full, complete, finished theory that is completely quantum mechanical. But we think it's out there. We think there is such a theory. It's just our job to find it. And when we have it, we will be able to understand where gravitons come from in that theory.
Take a quick break. If you like this episode, I'd really, really appreciate it. It would mean so much to me. Please share it with your friends and subscribe to the podcast. Email me at altucher@gmail.com and tell me why you subscribed. Thanks. I have to say, Airbnb has changed my life. I just love staying in Airbnbs. Like in about a month, I'm going to Cocoa Beach, which is right next to Cape Canaveral. I'm going to watch some rocket launches. I'm going to, of course, be staying in a very nice Airbnb on the beach. And it's just such a great experience. Like the whole world is available to us now because of Airbnb. But whenever I'm at an Airbnb, I always realize, the home that I left to come to this Airbnb, I could be making money on that right now by hosting and being an Airbnb myself. So, and I've known people, I had a friend who basically, made a living from turning his home into an Airbnb. So if you have a home, but you're not always at home, you do have an Airbnb there. And it can easily fit into your lifestyle, and it's a great way to earn some money. Your home might be worth more than you think. Find out how much at airbnb.com/host. The famous Abraham Lincoln quote says, "Good things come to those who wait." I wonder, did he really say that? Jay, did he really say that? Can you look that up? Regardless of who said it, that's only part of the quote. The full quote is, "Good things come to those who wait, but only the things left by those who hustle." Well, if you're a business owner and want the best people on your team, the same applies. And listen, I've interviewed 1,500 people now and a lot of entrepreneurs. I can safely say the one thing consistent among all entrepreneurs and CEOs, the successful ones, is that it's all about the people you surround yourself. If you hire well, you're going to have a great business. And, thankfully, ZipRecruiter puts the hustle in your hiring. So you find qualified candidates fast. This is so important, and I want you to try it. You could try it as a potential employer or employee. You can try it for free at ZipRecruiter.com/James. ZipRecruiter's smart technology finds top talent for your roles right away. Immediately after you post your job, if you're hiring, ZipRecruiter's matching technology starts showing you qualified people for it. And I will tell you that I signed up on ZipRecruiter as a potential employee. I just wanted to see how it works. And right away, it started matching me with really amazing potential employers. So give it a try at ZipRecruiter.com/James. Let ZipRecruiter give you the hiring hustle you need. See why 4 out of 5 employers who post on ZipRecruiter get a quality candidate within the first day. Just go to ZipRecruiter.com/James to try it for free. Again, that's ZipRecruiter.com/James. ZipRecruiter, the smartest way to hire. I read once an article where, and again, this is going to demonstrate my complete lack of knowledge or how little knowledge is a dangerous thing. But I read once, and this was in a physics article, that one theory of even the beginning of the universe is that sometimes it's a multi-universe theory, and sometimes these universes like crash into each other or intersect, and gravity, because it's such a weak force in this universe, might be a stronger force in some other universe that collided with this one. So that was a legit physics theory that I read.
No, it is absolutely. And even crazier ones are out there. But just to be sure, that's a highly speculative theory that the chances that it's going to end up being right are pretty small. That's okay. That's what we do in science, whether it's physics or anything else. We make hypotheses. We conjecture maybe things are like this, maybe are some other way. And then we ask, how would we know? How would we interpret that in terms of what we can observe about the universe, et cetera? And when it comes to the origin of the universe, the Big Bang, things like that, there's so much that we don't know that I think we're going to be speculating for quite a while longer.
So we know a couple things, though, right? We know that the universe can't have been like this forever. It can't be like how it is now for infinity in the past and infinity in the future, because it's been expanding. At some point, it must have been infinitesimally small, or not quite infinitesimally small, but much smaller than it is now. So we know that.
What we know is that the universe is much denser and hotter in the past. In fact, we have really good evidence for that, because when you make something hot and dense, it glows. And our early universe glowed, and we can see that radiation left over from the glow of the early universe. It's called the cosmic microwave background radiation. The outer space is suffused with microwaves. They won't heat you up if you're out there. In fact, it's quite cold, but they are the leftover evidence of the hot, dense early state, which we identify with the Big Bang. It was about 14 billion years ago. And the universe is still expanding, and as far as we know, it's going to keep expanding, maybe forever. So it looks like the universe just gets sort of colder and emptier as time goes on.
But isn't your theory that there's been many of these Big Bangs in the past? Does that mean that at some point there's a reduction until it gets dense again and then it explodes outwards? Or what's your version of the beginning of the universe?
Yeah, so I have my own speculative scenarios, which again, no one should take too seriously, but they're fun to think about, and who knows, they might end up being right. But in ours, there's no contraction. It's not like you bang and then you expand, but then you recollapse and contract again. That is a kind of universe that other people have talked about, the cyclic kind of universe. It's an old story. In our picture, when I say ours, this is a story I put forward in 2004 with Jennifer Chen, who was a graduate student at the time. We said, look, maybe there's only expansion and then little creation of new universes out of empty space. So the picture is, our universe expands and cools and empties out. But there is quantum mechanics, and quantum mechanics says that there are random things happening. There are things you can't quite predict. And that might include, in this speculative story, a bubble of an entirely new universe separating from ours and going its own way. So from our point of view in the big universe where we live now, it would look like a black hole briefly formed and then disappeared and made a little explosion, not very big, not, cosmic size, like a grenade going off or something like that. But from the inside, it would look like a tiny infinitesimal new universe had been created. And then that universe will expand and cool and empty out. And both our original universe and the new one can give rise to their own baby universes in the future, as we call them. So this is a way for the universe to keep regenerating without ever collapsing and crunching.
So that's interesting. So I've read that in so-called empty space, like out there in the middle of the universe, particles sometimes appear for just a microsecond, a nanosecond, and then disappear. And I was going to ask you about that, but what you're saying is over a sufficient enough time, trillions of years, quadrillions of years, who knows, enough random particles might accidentally appear at the same point in time that it's so dense that it explodes and creates its own Big Bang and its own universe inside that.
Yeah, that's exactly right. And the difference, these are hard things to talk about in ordinary English language because the language that we talk was not invented to think about these ideas. So there's a little bit of fuzziness and trying to put words onto the equations that underlie what we're saying here. But yes, the idea is not just particles popping in and out of existence, but whole universes popping in and out of existence. And that's made possible by Einstein's insight that space-time itself is curved and dynamical and changing.
And so, okay, so back to classical physics for a second, there's this notion of conservation that all the energy in the universe kind of remains constant. So when let's say I push you, I use some energy, but now the energy has left me, and now you're falling backwards. You have the energy, so the energy has got, and then you fall on the ground. Now the ground has the energy and it's absorbed by the earth, so it doesn't seem like a lot, but it's still around. Now, how could particles just appear out of nowhere if there's a conservation of energy?
Perfectly fair, and there's. Again, I hate to say this over and over again, but the equations are perfectly clear about this. It's just that our ordinary language fails us a little bit. But the answer is that gravity has a negative energy. So if you think about, I don't know what a good analogy is, but if you think about a hydrogen atom is an electrically charged electron around the nucleus, which is just a proton. And that hydrogen atom has less mass than the electron plus the proton by themselves. So you take an electron and a proton, two particles, both with mass, you combine them to get a hydrogen atom and the mass went down. What happened? The answer is that there's sort of a negative energy because their electric fields canceled each other out. And something very similar happens with gravity. You can have a whole universe full of stuff, but if that universe closes in on itself, then the total energy in that universe turns out to be exactly zero. A universe is actually cheap. You can make them without costing yourself anything. There's no total charge, no momentum, no energy, nothing like that. You can make a whole new universe. We're still sort of struggling to figure out what that means and what it implies for cosmology, but that seems to be what the math is telling us.
So in the sense of creating particles out of nothing, are you saying that sometimes maybe one field overwhelms another, and so in some point in distant space, a particle is that matches certain constraints that even helps even things out.
Yeah.
So particles are just randomly created all the time.
That's exactly right. And, it's subtle because we're talking about quantum mechanics here, and people don't, even professional physicists, completely understand quantum mechanics very famously. But we have examples where there are these so-called quantum fluctuations, and you can't predict exactly what the outcome of a measurement is going to be. You can't say that space, for example, is completely empty. You can put empty space in as empty a state as it possibly can be, but if then you look at it, if you say, okay, I'm going to measure the number of particles here in empty space, the answer is not necessarily zero. It might be zero most of the time, but there's a non-zero chance that you see particles there. And that's just what quantum mechanics forces you to believe.
So, and this is where we start to get to what I think is like the hardest question to wrap one's head around, but it's the most famous question in quantum mechanics, which is, I'm just going to ask it at a very high level, why does observing a very small particle change the particle?
Good. Well, we wish we knew the answer to that one. I mean, in fact,
And you this is your whole book talks
Yeah,
about
I
this.
know.
and I see the history of it. I see when they're talking, and I'm just trying to express to the reader, the book is readable and it's understandable, but still, when you try to bring it back to the highest level question, it's hard to grasp.
yeah. Well, and like I said, physicists disagree about the answer to this question. What happens when you measure the position or something like that of a tiny little quantum particle? This is famously called the measurement problem of quantum mechanics. And what we know is that when you measure the particle, we can make a prediction for what you'll see. We're very, very good at that. But then if you ask, okay, what happened in the course of that measurement? What is actually going on? That we disagree with each other about. My story would be that you are a quantum mechanical system also. The particle is a quantum mechanical system, but so are you. And what you mean by measure the position of the particle is actually you become entangled with the particle's quantum mechanical state. Entanglement is this weird feature of quantum mechanics that was invented by Einstein and his collaborators. And it says that different parts of the universe can have physical states that are connected to each other in a uniquely quantum mechanical way. But other people would say completely different stories about what it means to measure something. So I think the one lesson that we can hold on to is that in quantum mechanics, different parts of the universe aren't as separate as we would have thought in classical mechanics. In classical mechanics, we have the sun and the earth and the moon and the other planets, and they're just totally separate things. They interact with each other, but you can tell me what the state, what the configuration, what the velocity of any one of those things is, and there's a unique answer. In quantum mechanics, it's not like that. There's a holistic kind of view of the universe. You have to tell me what the state of everything at once really is.
And so I like this view, though, of not just, like I always think of, there's this separation between classical physics and quantum mechanics in that one deals with very small objects, the other deals with objects like the sun and the moon and so on. But obviously, if there's going to be one theory to so-called unify them all, we all have to, we're giant clusters of quantum particles, so the rules of quantum mechanics must affect us. So you're saying that perhaps when a scientist, or let's say when I measure something, there's some, just like when the apple falls from the tree to the ground, there's some relationship between the ground and the apple that is causing this interaction. Perhaps there's some field between myself and the small particle that is causing like a weird kind of measurement gravity.
Yeah.
Like my like information itself is some kind of particle or quantum thing.
That's right. And this is exactly the source of the great debates between Einstein and Bohr that happened in the 1920s and that modern physicists are continuing on with. Are you correctly described by the rules of quantum mechanics? Like you said, and like I completely agree with, I'm made of atoms. You're made of atoms. The atoms obey the rules of quantum mechanics. Of course, I should also obey the rules of quantum mechanics. Now, it's also true that I obey the rules of classical mechanics, and that's allowed because I am a big, massive thing. As things become larger and larger, classical mechanics becomes a better and better approximation to quantum mechanics. So it's not that quantum mechanics describes the very small things and classical mechanics describes very large things. Quantum mechanics describes everything. And when things are very small, there's no good classical approximation. And when they're very large, there is.
Okay, so one step further, the fact that I observe something about a particle changes it, that is related to this theory of what's called spooky entanglement, right? So that if two particles, let's say, or one bigger particle was split apart, so that the particle, so now it's two particles and they're exactly alike, but one has a negative charge, the other has a positive charge, and they're sent in opposite directions at the speed of light. So let's say they're 10 light years apart. There's this whole idea that if you observe one, now you know simultaneously information that just occurred about the other. Because you observed it, you changed the first particle, but now you know the other particle that's 10 light years away has instantly changed. And there's this question of how could it do that? That means the information traveled at faster than the speed of light to get to that particle in order to change it. And your point is that actually you can't tell the person on the other side, the person who has the other particle, let's say, it still requires 10 light years to get information to him at least. My question on that, though, is what if they both observe at the exact same moment in time?
So good. Yeah, you're describing exactly what bothered Albert Einstein about the usual way of talking about quantum mechanics.
A lot of people compare me to Einstein.
It's very similar.
But,
I know. I'm glad you're leaning into that. It's better to talk about the spin of the particle rather than the charge, because the charge is sort of something that you notice right away. But a particle can spin clockwise or counterclockwise. And in quantum mechanics, it can be in what we call a superposition. It can be in a combination of spinning clockwise and counterclockwise, so that until you measure it, there's no fact of the matter about which it's doing. You can predict there's a probability, 50% that I'll see clockwise, 50% that I'll see counterclockwise. And like you say, they can have two particles that are entangled, and they can be entangled in such a way that for neither one do I know what answer I'm going to get when I ask which way it's spinning. But I know that if I measure both of them, I will get the opposite answer. So if one is spinning clockwise, the other is spinning counterclockwise. And that's true even if you move the particles 10 light years apart. And then that's exactly the mystery that we have verified experimentally that it's true, but we don't know the right way of talking about it. That if I measure them at the same time, we have to be careful of what even that means in relativity, but let's imagine we answer that question. So
okay, but even within seconds of each other, because they're 10 light years apart, so it doesn't matter that much.
Yeah, so we measure them more or less the same time, and even though we don't know what either person is going to observe, we know that they're going to observe the opposite ones. So if Alice, who has the first particle, measures a fraction of a second earlier and she gets clockwise, then Bob, who's going to measure later, is definitely going to get counterclockwise. It sure sounds like information has gone from one particle to another faster than the speed of light. Maybe it has. That's exactly what we don't agree on in quantum mechanics. What we do agree on is you can't use that to send a signal, precisely because, as you said, even if Alice measures that her spin is clockwise, she knows what Bob is going to get. But Bob doesn't know what he's going to get until he actually does it. He's no the wiser. So it's not a useful way of telephoning somebody faster than the speed of light.
I guess because can you manipulate what you're measuring so that it comes out a certain way? I guess that would be a message.
Right, but
a message involves someone manipulating on one side, like I send Morse code, so I manipulate a piece of paper to have dots in it that I run through a machine. But you can't manipulate the particle, you could just observe the particle.
Exactly. So if Alice has her particle and it's in a state where it's 50% likely to be spin clockwise and 50% counterclockwise, if she could do some clever measuring process that would guarantee that she gets clockwise, then she's basically forcing Bob to get counterclockwise, and that's information he can use. But she can't. There are theorems in quantum mechanics that say there's no clever way to force the measurement outcome when it's a 50-50 chance. You always have to just rely on the random numbers. So you can literally prove a theorem that says you can't send information this way.
But the fact that Alice observed the particle did, as you say, it made the quote-unquote wave function collapse. So now it actually has a direction to its spin. Prior to Alice observing it did not have a direction. So now suddenly Bob's particle also has a direction faster than the 10 light years that it would imply to get that information. And so what I'm wondering is, like you mentioned before, that gravity works because Einstein started looking at space-time as 4 dimensions, including time. I wonder if there's like an information 5th dimension, and maybe that's, I'm just making this up. I'm being an idiot.
Well, no, not at all. But it's actually much worse than that. It's worse than the 5th dimension. It's that space where we live, the 3-dimensional space where you and I live, is not that fundamental in quantum mechanics. It's not the central thing. The mathematics of quantum mechanics suggests that the space that describes our universe is enormously bigger than three-dimensional space. It's a space called Hilbert space. You can read about it in my book. I'm not going to get into details. But the point is that the universe is much richer and more complicated than a bunch of stuff distributed in three-dimensional space. That is exactly what you need to account for what we observe in quantum theory.
Don't just ride the index, seek to outperform it with Fidelity Active ETFs. Learn more at fidelity.com/active ETFs. Before investing in any exchange-traded fund, you should consider its investment objectives, risks, charges, and expenses. Contact Fidelity for a prospectus, an offering circular, or if available, a summary prospectus containing this information. Read it carefully. While active ETFs offer the potential to outperform an index, these products may more significantly trail an index as compared with passive ETFs. Fidelity Brokerage Services, LLC, member NYSE, SIPC.
Two guys drove to work. Neither guy wore a seatbelt. One guy got a ticket. One guy didn't. The same two guys drove home. One guy wore a seatbelt. One guy didn't. One guy made it home. The guy not wearing his seatbelt didn't. Don't risk it. Click it or ticket. Paid for by NHTSA.
This will be my final stupid question because I have other questions related to the book and related to your background and so on. But maybe every type of field or every type of interaction between particles creates a new kind of curvature.
Maybe. At this point, I'm going to just encourage you to write down your theory and submit it to a physics
I'm
journal.
I don't know how to do
better than that. Yeah, good. You'll remember this. You'll acknowledge me in your speech.
How did you get interested in all of this stuff? And why this route as opposed to, let's say, more experimental physics or more theoretical physics? You're somewhere in the middle of like cosmological physics.
Yeah, I was a kid. I was like 10 years old when I just started reading books in the local public library about the Big Bang and black holes and all these particles that have been discovered in the 60s and 70s. And I just fell in love with it right away, and I never sort of deviated from that. As I grew up and went to school, et cetera, I developed extra interests in more the philosophical side of physics and also in sort of more everyday things, complex systems and entropy and things like that. And so, I think that I'm not done evolving yet, but I definitely early on picked the right thing for me to specialize in.
What is the philosophical side of physics? Because I think that's misunderstood as well.
Yeah, I think that the way that I think about it is that philosophers are just super concerned about getting all the details right, about making sure that we're not sloppy. Like I told the joke in my first book that physicists get frustrated with philosophers because they're always asking about the meaning of different words. And philosophers get frustrated with physicists because they keep using words without saying what they mean. And you can be frustrated both ways, right? It's a different perspective on things. But like when you say, what is an event? What does it mean for something to cause something else? What does it mean for something to happen in the universe? What really exists? All of these questions, physicists will not want to answer. They're like, that's boring. That's not what I do for a living. That's just fussing around. And philosophers will be infinitely patient with figuring out exactly what is meant by those. And I think that when you're talking about the difficult questions of cosmology or quantum mechanics, you need both perspectives.
Why?
Well, because physicists are happy to get the right answer even if it's for the wrong reasons. And that works fine as long as you know what the right answer is. But for something like the origin of the universe, we can't see it. We can't go and do an experiment that shows us what happened at the origin of the universe. So if we're going to talk about it intelligently, we better be very, very sure that we know what we're talking about and we're not being sloppy.
So you have to develop a kind of psychology of being comfortable in a scientific theory where you're trying to prove things. You have to be comfortable with uncertainty. The fact that large aspects of this scientific theory are not able to, there's no proofs. There's no solid understanding of truth.
Well, absolutely. I think that scientists should always recognize that they don't prove things. You don't ever establish the once and for all final 100% metaphysical certainty of any scientific claim. And the reason why is because tomorrow you might do an experiment that disagrees with it, right? So that's okay. Like you say, you have to live with that uncertainty, with that ambiguity. We think that we get more and more confident in the parts of our understandings that are better and better established, but we never reach 100%.
Do we have, like right now, at first people thought the smallest type of particle was an atom. And then we realized, an atom has protons and neutrons, and then even smaller is the electron. Now all these things have quarks, which are even smaller. And then there's particles like the neutrino, which is, the mass is so small, there's been unable to measure it. Could there be particles that they're so small we can't even theorize them, let alone detect them?
Well, nothing ever stops us from theorizing them. People have absolutely theorized that quarks or electrons, for example, are made of even smaller particles. So far, attempts to do that have not panned out very well. They've made predictions that have not come true in other experiments. So my own personal guess is that there will be something more fundamental than what we call quarks or electrons, but it won't be something as simple and straightforward as even tinier particles. It'll be something more profound than that.
Profound. So you have an idea then what you're thinking about, but what do you mean?
Well, I think that the way that, again, and this is where philosophy comes in, if you take quantum mechanics seriously, like we were saying before, it suggests a radically different view of the world, mathematically or conceptually or whatever you want to call it. And I think that we human beings and even we physicists have not quite come to peace with that radical new view of the world suggested by quantum mechanics. We still rely on our classical intuitions. We start with point particles or fields or billiard balls or whatever, and we apply the rules of quantum mechanics to them. But nature doesn't do that. Nature just is quantum mechanical from the start. So my own conjecture is that the way forward will be to start purely quantum mechanical, not talking about space or time or particles or forces or any of those things, just talking about the quantum mechanical wave function of the universe and seeing how it can possibly lead to the world we see around us.
Now, when you were, like in any academic discipline, there's ideas and proofs, but there's also politics. So sometimes the loudest get heard the most, or the ones who are influencing publications in various journals and so on. So does that, for you, and for many academics who just want to focus on the ideas and the theories and so on, does it ever get frustrating? Like in 2006, when you initially were going for tenure, you got denied. How did that affect your worldview? You were interested in this since you were 10 years old. Now suddenly someone told you, look, we're not going to let you do what you love anymore.
Yeah, no, I mean, it's absolutely a blow when something like that happens. I mean, happily for me, other people were immediately stepping up and saying, well, we'll let you do it. So it wasn't actually, kicked out of the field in any possible way. But there's different, like you say, there is politics. And what that means is that, to put it in a less contentious way, there are judgments that come in to what people you pay attention to, what theories you take seriously, what ideas are nurtured and developed and supported, and which ideas are ignored. And those things are going to change with time, and they're actually even going to change with location. Some universities like certain kinds of physics more than others do. And so you have to, that's inevitable. There's no way around that, because physics or science more generally are human endeavors. They're done by human beings. So all of the shortcomings and foibles that human beings have, scientists have too.
And like you mentioned, I mean, right now you're a tenured professor at Johns Hopkins, so you landed on your feet instantly and after the tenure stuff. But why do you think you didn't get tenure that first time? Like how does one get tenure?
Well, it's all very mysterious, right? There's no public record, so I actually can't tell you with any reliability why it is. There's various people who are on the faculty who gave me their perspectives, but they were all very different from each other, so I don't know what the coherent picture is. I mean, one thing that was certainly part of it is that I did things other than physics research. I wrote a textbook in general relativity, and that's not considered to be the kind of thing you should do before you get tenure. Certain other people just didn't like the kind of research that I did. It was that simple. So that, in a sense, that doesn't bother me. Like these are judgment calls, and that's perfectly okay. I do think that the criteria should be a bit more transparent, and the process should be more transparent. But universities think they're doing fine. This is not a high priority agenda item for them.
And so I'm curious. Like, obviously, you're very smart. You've written these best-selling books about topics that are inconceivable to almost everybody. And I always am curious about this. I feel like if I was transported back in time 1,000 years, and let's say I just ended up in, the 1400s in England or in the 800s in England, and I just landed on a field, and then I had to survive, I have actually no skills. Like, I could turn on Zoom.
Podcasting is not helpful? Yeah.
Well, maybe it is, because maybe I can talk my way out of being killed instantly.
There you go.
I don't know. But you're an eminent scientist. Are there skills that if you were in 800 AD, assuming you speak the language of everybody, how would you survive? What could you do? Can you make a light for people, an electric light?
No, I'm a pretty darn theoretical physicist. So my practical skills are very, very low. Anyone who, putters around the house is going to be more handy and useful at that kind of thing than I would be back in the ancient times. What I would try to do if they had, the technology to write books, I would try to quickly write down everything I could think about as far as physics is concerned. I would explain calculus and Newtonian mechanics and electromagnetism and things like that. And I do actually think that would be very useful in the long term. It would not exactly lead to a better light bulb right away, but I think it would accelerate the development of stuff like that.
Could it be useful in a battle? Like, so you would know the exact arc you could aim a cannon, or did they already know that?
It is useful in a battle. Famously, Karl Schwarzschild, who was the German astronomer who first solved the equations of general relativity written down by Albert Einstein, was working at the Russian front. It was in World War I when he was doing this. It was 1916, 1917. And his job was calculating the trajectories of artillery shells. And so day job, artillery shells, night job, solving the equations for the curvature of spacetime.
That's interesting. I'll have to read about him. And now here's a random question that I've just been wondering about, and maybe a smart person could tell me. When I don't know anything about cars. I don't drive. When I go on the highway, my wife's driving, and I look at the other cars, they all look exactly the same to me. So every SUV looks like every other SUV.
Yeah.
And in general, most cars look pretty ugly, and they look like each other. Why can't people why don't people experiment more with car design? It shouldn't be that hard, and you can make really pretty looking cars maybe.
I'm with you. Like, this is not my area of expertise. No one's asking me for my input, but
I'm asking you for your input.
Okay, good. Finally. I do have friends like Jason Torchinsky, who is an automotive expert. He writes for The Autopian, and he has a long-running rant about the colors of cars. If you see pictures of a parking lot in the 70s, it was alive with color. There were orange cars and green cars and red cars and whatever. And now every car is white, gray, or black, 90% of them.
Yeah.
And maybe a dull beige. And, who made that decision? It's very unclear. But I agree with your point, too. Like, even not just the colors, but the actual designs of the cars are super unimaginative. We own a BMW i3, which is this cute little electric car that looks very different than other cars. And that's kind of why we like it. But of course, they canceled it because they didn't want to support that weirdness.
Yeah, it's like I was a fan, this is like 20 years ago, of the PT Cruiser. So it was a Chrysler car that looked a little bit different from all the other cars. And
garish purple.
And the same thing happens in like architecture. Like if you go to buildings made in the 1600s, they're like beautiful and ornate, and there's like columns on them, and the doors have pretty shapes, and then you go to a building now. Okay, they try to be creative, but basically, you when you picture an office building in your head, you always picture the exact same building. It's just this straight up rectangle, cube, whatever. So maybe as many fields advance, it gets harder to be creative, or maybe there's so much institutional pressure to be the same, so you keep your job because there's a lot more people in that industry, and so everybody wants to, it's like the whole you can't get fired if you buy from IBM sort of thing. You can't get fired if you design just a generic looking office building.
Look, I think a lot of it is just profit motive, right? It's capitalism at work, because the thing about buildings is that back in the day when you were building a cathedral, it was necessarily expensive. There was a lot of labor involved. They were putting every brick down by hand or whatever. And so adding a few gargoyles didn't make that much difference. It was just, part of the overall cost that you'd have to pay anyway. These days, we have much cheaper ways of making buildings. Just get some giant steel girders, lay down some concrete. And so now making buildings fancy and individualistic and artistic is a huge extra cost. And that goes for everything. Why make cars different than everybody else? Well, we know that people buy these kinds of cars, right? It's a weird thing where technology allows for the possibility of endless variety, but then to make money, we do it we often deploy the technology in fairly humdrum ways.
So that's a good answer. So basically, because technology has improved, the resources for creativity have gotten greater, but because things have gotten so much cheaper to make everything, like it's, for instance, cheaper to make electricity. This is a number that's commonly measured through the years. If you don't make things as cheap as your competitors, they will eventually beat you out in costs and are able to hire better people because of that, and move ahead of you. So that could be that's a very good answer. And so, but I'm wondering then, how does one inject creativity? So even in a field like physics, when you want to inject creativity, how do you do it? Without, because you're not subject to the laws of capitalism in the same way, but maybe you are, because you have to publish where everyone else is publishing. And so it's the same kind of forces. There's so many spots, and there's going to be competition for them, and you have to make yourself in there. So how do you personally inject creativity or think about things in a creative way in physics?
Yeah, it's absolutely true. Like, the profit motive is not there, but you do have to get things published. You have to get grant funding. You have to get a job, which is very hard to do. And so there's a weird dichotomy where we have the academic system with professors and tenure, where once you're a senior established person, you have a lot of flexibility. Like, you can work on what you want to work on. You can have a crazy creative idea and pursue it. But when you're a young person, in the days when you actually have wacky creative ideas, you don't have any security whatsoever. And in fact, you had better do things that are considered acceptable by the people in power, right? So we have invented a system where you can be creative, but the people who are actually creative often don't make it that far enough to enjoy the fruits of that. So I don't know how to do it better. Most people who think that they're super creative and disruptive are actually just wrong. So you can't just say, let all the creative people be in charge. You need some solid people also. And, compromising between that is a tricky thing.
And do you think also that is created, like, so younger people, they have to kind of toe the line, get published, and so on. So it's a little harder. It's a little harder for them to be creative right at the point where scientifically it's been shown, in the sciences, younger people are more creative. Einstein, his most cited work is his works about quantum mechanics in the 1920s, but of course his most creative work was probably the theory of relativity and the things he won the Nobel Prize for when he was younger in his 20s. And so do you feel for yourself like, oh, I've passed my peak age of scientific discovery, so have you transitioned into, well, obviously you've transitioned a little bit into mentorship and teaching because you're writing these books and so on for the masses and trying to teach. But does that ever concern you that you're peak moments of physics creativity might be behind you?
Well, I think that my saving grace is that I'm very, very slow. So I think that only now in my 50s am I finally discovering what I should have been working on when I was back in my 20s. It took me a long time to figure out what the exciting areas of science are that I have something to contribute to. So I personally think that I'm, beginning my career right now, really. I mean, it's true that I am stretched thin by trying to do other things like write books and have podcasts and teach courses and things like that, but all that's fun and it's good. And I just need to carve out that time to be creative and to try to do some good science.
And what area is exciting you? Is that explainable?
Yeah, I alluded to it a little bit earlier when I mentioned complexity and emergence. The idea that we have a very simple set of underlying laws of physics with particles and forces just doing their things. And somehow out of this grows this enormous complexity of the world around us. I mean, biological organisms are, the most obvious example of complex systems. And they come into being despite the fact that entropy is increasing. There's this famous rule of physics, the second law of thermodynamics, that says the disorderliness or disorganization of the universe grows with time. And so that's in a little bit of tension with the fact that life comes into existence and other complicated things like, the galaxy, the Milky Way galaxy comes into existence. So I'm working to understand that tension, how you can get impersonal, undirected, mechanical underlying laws of physics giving rise to all the beautiful complexity of you and me.
It seems like the rise in entropy might increase the possibility of life and existence occurring. So you take it you mentioned biology. Humans exist because of the increased complexity of our bodies and evolution. More mutations happen, and those random mutations, the good features survive, and over a billion years have created us.
That's true. So I think that the way to say that is that the fact that entropy is increasing allows for the development and flourishing of complexity. But it doesn't imply it, right? It doesn't mean that it's necessarily going to happen. So a better scientific understanding of exactly what conditions you need for complexity to arise, what the laws of physics have to be, what the initial conditions have to be, is it generic and robust, or is it very fragile and particular and fine-tuned? I don't think any of these questions have firm answers right now.
Well, it's all fascinating stuff, and thank you for agreeing to talk to me. I know I really didn't do your book and ideas justice, but I just want to understand these things, and I love reading about it. I love reading your stuff, and this book, The Biggest Ideas in the Universe, Quanta and Fields, and this file follows your earlier book, The Biggest Ideas in the Universe. I don't know what the subtitle was of that one. Did it have a subtitle?
Space, Time, and Motion.
It's a good subtitle, Space, Time, and Motion. This one's Quanta and Fields. And you also have your podcast, Mindscape, where you explore a lot of these things across many different, types of science. And I encourage people to listen to that as well.
Great. Thanks very much, James. It's a lot of fun to be on.
Yeah, thank you.
Don't just ride the index, seek to outperform it with Fidelity Active ETFs. Learn more at fidelity.com/active ETFs. Before investing in any exchange-traded fund, you should consider its investment objectives, risks, charges, and expenses. Contact Fidelity for a prospectus, an offering circular, or if available, a summary prospectus containing this information. Read it carefully. While active ETFs offer the potential to outperform an index, these products may more significantly trail an index as compared with passive ETFs. Fidelity Brokerage Services, LLC, member NYSE, SIPC.
Two guys drove to work. Neither guy wore a seatbelt. One guy got a ticket. One guy didn't. The same two guys drove home. One guy wore a seatbelt. One guy didn't. One guy made it home. The guy not wearing his seatbelt didn't. Don't risk it. Click it or ticket. Paid for by NHTSA.